Hello everyone, in this video I'm going to show how to analyze a business case using KNN algorithm and using Analytic Solver. Janet Williams, the membership manager at 24/7 Fitness Center, has collected data from 1000 past open house attendees, which is in Gym Data Worksheet, and 23 new open house attendees, which is in Gym Score Worksheet. The data include the age and the annual income of the attendee, the average number of hours that the attendee exercises per week, and for the gym data worksheet, we have here the column called Enroll, which shows whether or not the attendee purchases a membership. Janet is interested in a model that will help her identify these new members who are likely to purchase a membership. As I discussed in the previous videos, Module 4 and Module 3, to develop and evaluate a classification model, we generally perform cross-validation using the holdout method. Analytic Solver provides a procedure for the holdout method and allows for partitioning a dataset into training, validation, and test dataset. In this example, I partition our dataset in Analytic Solver as follows: 50% for training, 30% for validation, and 20% for test. So to perform KNN algorithm, we need to first partition the dataset. Here click on data mining and then click partition and then standard partition. Make sure that the dataset is selected. Here it's from A1 to D1001. And also make sure that first row contains headers is checked. The variables in input data box will populate once you select the data. Select and move all the variables to the selected variables box. And then click pick up rows randomly and choose specify percentages. And here enter 50% for training set, 30% for validation, and 20% for the test dataset. Accept other defaults and click OK. Analytic Solver will create a new worksheet called STD partition. In the partition summary table here, you would see that training dataset has 500 records, validation has 300, and testing has 200 records. Now we are going to perform KNN algorithm. Again, data mining, and then classify, and here choose K nearest neighbors. Make sure that here STD partition worksheet is active. In the data tab, select to move age, income, and hours to the selected variables box. Select enroll as output variable. Accept the other defaults and click next. In the parameters tab, click to rescale data. Check the rescale data checkbox. Select standardization and then click done. In the number neighbors K box, input 10, and under nearest neighbors search, select search 1 to K. Analytic Solver will repeat the KNN algorithm with the values of K from 1 to 10, but only the K value that yields the best result will be used in subsequent steps. Click next. In the scoring tab, check the summary report boxes for training, validation, and test dataset. Also check lift charts box for the score test data. Check the in worksheet. Under the new data WS tab, select gym score in the worksheet box and enter A1 to C24 in the data range. Make sure first row contains headers is checked. These 23 records of potential members will be scored by the KNN classification algorithm. And then click Match by Name. And then click Finish. Analytic Solver will create 7 new worksheets. The KNNC underscore output worksheet displays the misclassification percentage for each value of K using the validation dataset. Recall from the previous videos that the misclassification rate is the overall proportion of cases that are classified incorrectly, false positives and false negatives combined. Here in this table, you see that the lowest misclassification rate is reached at the K value of 3, which is 8%. Therefore, K is equal to 3 is used in the subsequent calculations. The KNNC underscore training score, the KNNC underscore validation score, and KNNC underscore test score worksheets display the classification results for the training, validation, and test datasets with K is equal to 3. Here, the tables on this screen summarizes the main results from the test dataset. We focus on most notable performance measures for this application. The accuracy rate indicates that 89.5% of the observations are correctly classified, thus 10.5 are incorrectly classified. Normally, the performance measures from the training data will be better than the results obtained from the validation or test data. However, if the performance values from the training data are considerably better than the values from the validation and the test data, then we might have the problem of overfitting. In the 24/7 Fitness Center, the KNN algorithm can accurately predict the outcome for training dataset 94.6% accuracy rate, or 94.6% of the observations in the training dataset is accurately classified. In validation dataset, 92% of the observations in the validation data is correctly identified. And as you see in the test dataset, the accuracy rate is slightly lower, which is 89.5%. This indicates that some overfitting may exist. However, the differences may not be large enough to suggest any severe overfitting problem. The sensitivity rate of 0.9 is the proportion of buyers that the model is identified correctly, while the specificity of 0.89 is the proportion of the non-buyers that the model is able to identify correctly. To answer the question of whether the resulting KNN model has good predictive performance or not, we can compare the accuracy rate of the model to that of the naive rule. In the naive rule, all cases are classified into the predominant class. For example, here in the test dataset, we have 80 target class, which means enrolled, out of 200 observations. The naive rule would assume that each case has the probability of 80 divided 200, which in this case equals to 0.4. That means 0.4 or 40% of the observations is belonging to target class. Our target class is the people who enroll to the gym. Using the cutoff value of 0.5, the naive rule will classify all cases into non-target case. Recall that if your probability is less than the cutoff value, then your predicted Y is going to be 0. Therefore, naive rule will classify all cases into non-target class, or do not enroll in the gym, and produce an accuracy rate of 200 minus 80 divided by 200, which is 0.6. Because 80 of them, the naive model is not going to correctly identify, but remaining 140 non-buyers will be correctly identified. Therefore, accuracy rate will be 0.6. And sensitivity will be 0 because none of the buyers will be identified. And specificity will be 1 because all of the non-buyers will be identified with the naive rule. Therefore, we conclude that KNN model has better predictive performance than the naive rule does, especially if our goal is to identify target class cases, because target class cases identified by the naive model is 0, whereas with our model, the sensitivity is 0.9, which means 90% of buyers are correctly identified. As I said in the previous videos, the choice of cutoff value can influence the confusion matrix and the resulting performance measures. By default, Analytic Solver uses 0.5 as the cutoff value for the binary choice models. The analyst may choose to increase or decrease the cutoff value to classify fewer or more observations into the target class. In this example, the opportunity cost of missing a potential gym member who would have purchased a gym membership is likely to be higher than the cost of reaching out a potential gym member who ends up not purchasing a gym membership. Furthermore, among the 1,000 past open house attendees in the dataset, 403 purchased gym memberships, suggesting that the probability of open house attendee purchasing the gym membership is 403 divided by 1,000, which is 0.403. So, an analyst may choose to use this cutoff value instead of 0.5. Next, we are going to analyze the performance of the models using charts. Here on the screen, you see 3 charts, and we start with the lift chart. In cumulative lift chart, the blue line represents the results from KNN algorithm, and the diagonal red line represents a model that randomly classifies potential gym members, which we call it as baseline. In this case, the blue line from the KNN model lies well above the red diagonal line, indicating that KNN model performs considerably better in terms of predicting whether or not potential gym members will purchase a gym membership as compared to the baseline model. The second chart is Deciled Wise Lift chart, and this chart shows that the first 10% of potential members selected by the KNN model include about 2.375 times as many individuals who would actually purchase a gym membership than a randomly selected 10% of potential members. Moreover, the decile-wise lift chart shows that almost all of the Class 1 cases, that is, purchased a gym membership, have been identified within the first 5 deciles of the cases, with the highest predicted probability of belonging to Class 1. Next, we look at the ROG curve, and ROG curve also lies well above the red diagonal line. The area on the ROG curve, or AUC, is very high, 0.9273, indicating that the KNN model performs extremely well in terms of sensitivity and specificity across all possible cutoff values. And next, we are going to check KNNC_new score worksheet. Here on this worksheet, you see that classification details table. In this table, the 23 records of potential members are scored. The prediction and roll column displays the classification result for each record. The KNN model predicts that of 6 of the 23 attendees will purchase a gym membership. Let's combine this information with the information we have in gym_score worksheet. Resulting this grouping, Janet and her staff should target the second attendee, a 23-year-old with an annual income of $65,000 who exercises 9 hours per week, as well as the last attendee, a 51-year-old with an annual income of $88,000 who exercises 6 hours per week. Most of the open house attendees that the KNN model classify as more likely to purchase a gym membership are individuals older than 50 years who either have a relatively high annual income or spend at least 9 hours on weekly exercise. This is how we analyze a business case using KNN algorithm.